So you've already seen many ways in which quantum entanglement is special. One of the most important of these is through the kind of very strong correlations that it can generate. And you saw how this was demonstrated through the ability of quantum players sharing entanglement to win with a higher success probability than classical pairs in some non-local games, such as the CHSH game. Now in this module, we're going to see another related property of entanglement called monogamy. Monogamy expresses the fact that these very strong correlations that entanglement lets you generate between two parties, these correlations in general cannot be extended to the same correlations shared between three parties. And I'll show you precisely how we can quantify this statement. But monogamy is really one of the most fundamental properties of entanglement. It's also one of the most interesting, one of the most intriguing. We'll see it over and over again throughout the course. In particular, monogamy forms the basis of security for a lot of quantum cryptography, and certainly for the task of quantum key distribution, on which we're going to focus on a little later on. Because monogamy says that as long as two parties can verify they are sharing a state that lets them generate sufficiently strong correlations, then as a consequence, these correlations cannot be shared. And as a further consequence, it means that no possible eavesdropper could similarly share strong correlations with the two original parties. So this is something that we'll make precise much later on, but now first let me describe a little bit more precisely what we mean by this monogamy of entanglement. So let's do some examples. Let's imagine that we have two parties, Alice and Bob, and to start with, Alice and Bob can share a different type of information. So for instance, they could just share a bit. This means that Alice has a certain bit. For instance, this bit could be a 0. Bob has the same bit. This bit can be a 0. And my question is, can this information that Alice and Bob have in common be shared with a third party, call her Eve? And the answer is yes, of course. I can copy this bit over. It is completely possible that Eve has the same bit as Alice and Bob. Alright, so that's for a fixed bit. Now let's think of a distribution. Imagine that Alice and Bob share a distribution. What does this mean? Let's imagine that they have a little box. Each of their boxes has a button, and when they press a button, a certain bit comes out, and these bits are jointly distributed according to a distribution which, for example, with probability a half would give a 0 to Alice and a 1 to Bob, and with probability a half would give a 1 to Alice and a 0 to Bob. So they're perfectly anti-correlated. Our question is, can these correlations between Alice and Bob be shared? Here there's a question of what I mean. What does it mean to share a distribution? Well, what I would like is, does there exist a joint distribution on three systems now, Alice, Bob, and Eve, so that this distribution has the following properties? The marginal distribution on Alice and Bob is as I described it here, and I would also like that the marginal distribution on Alice and Eve is also the same. So I have to write something for Eve in a way that if I look at the marginal of the joint distribution in this blue box, I recover the same thing as the other blue box. In this way, I'll say that the correlations between Alice and Bob are shared also between Alice and Eve. Eve and Bob are interchangeable. So is this possible or not? Well, in this example, it is. What I can do is simply duplicate Bob. So I will say that now my tripartite probability distribution is that with probability half, Alice has a 0, Bob has a 1, and Eve also has a 1. And with probability half, Alice has a 1, Bob has a 0, and Eve also has a 0. So there's no problem in sharing a distribution. I just copy over Bob's bit to Eve. Okay, so that's for classical information. Let's see if we can share quantum correlations now. Let's start with a qubit. Let's imagine that Alice has a qubit initialized in the plus state. Bob has a qubit initialized also, let's say, in the plus state, so they share this plus qubit. Is it possible for Eve to have the same information as Bob with respect to Alice? Yeah, of course it is possible. I'll just give Eve a plus and there's no problem. Okay, that's for tensor product state. How about the case where Alice and Bob share an entangled state? Let's take some kind of a complicated entangled state. For instance, the state could be root 1/3, 0 for Alice, and a plus for Bob, plus root 2/3, 1 for Alice, and a minus for Bob. Note that the decomposition of the state that I am giving to you is the Schmidt decomposition, so I'm giving it to you in the simplest possible form. Now, is it possible to create a tripartite state now, such that the tripartite state on A and B looks exactly as I've written it here, but also on A and E, it would look the same, right? So I would like a psi ABC such that if I look at the reduced density on A and B, I recover the state that's here, and I recover the same state if I look at the reduced density on A and E. Okay, I'll let you think about it. Can you do it? Okay, so I claim that you can't. This is impossible. Let's see why. Let's try to do it, and then let's see why it's impossible. Let's try to do it in a general case. So I'll just take a state psi that's written in its Schmidt decomposition as lambda 0, 0, 0 plus lambda 1, 1, 1. In general, this 0 and this 1 could be arbitrary bases for the A and B systems, but since I can just change those by applying local unitaries, our task is the same if I start with this state here. Now we could do the same trick that we tried to use to do for the probability distribution, which is simply copy over Bob's qubit to Eve. So it would be natural to define a state psi on A, B, and C, which would be equal to lambda 0, 0, 0, 0, plus lambda 1, 1, 1, 1. And it looks like if I do this, then yes, I've managed to share Alice and Bob's correlations with Eve. Right? If Alice and Bob had a 0, Eve also has a 0. If Alice and Bob had a 1, Eve also has a 1. If I say this, I'm repeating the same reasoning as in the classical case, and I'm only going to the point where I can say that they would be sharing the same classical correlations. That's not the requirement that I wanted. I want this joint state to reproduce, with its reduced density matrices, the original state that I started from. So we need to compute the reduced densities. So let's do it. Let's compute the reduced density of psi on A and B. So I let rho ABC to be psi rank 1, and I want to compute the reduced density. So we need to trace out C. Let's measure C in the computational basis. What do we get? With probability lambda 0 squared, A and B are in the joint state 0, 0. And with probability lambda 1 squared, they're in the state 1, 1. Now, are these two states the same? Well, no, they're not, right? This one here is a separable state. Rho AB is just a uniform mixture of tensor product states. It's separable. Psi AB is entangled. Unless lambda 0 is 1, lambda 1 is 0, or vice versa, the Schmidt rank is larger than 1, so there's entanglement in that state. So the two are not the same. We have not succeeded. And now if you think a little bit more, a consequence of this is that no state that is entangled can be shared. And the reason for this is that here, if the state is entangled between Alice and Bob, and I want the same state to be entangled between Alice and Eve, it means that there's entanglement between Alice and Eve in my tripartite state phi ABC. If there's entanglement between Alice and Eve in that state, when I trace out C, I'm not going to get a pure state. There's entanglement. The Schmidt rank is bigger than 1, I'm going to get a mixed state. Which means that if there's entanglement in phi between A and C, then the reduced density on AB cannot be a pure state. It has to be a mixed state. In particular, it cannot be this pure entangled state that I started from. So it's simply impossible to share entanglement in the sense that I'm describing here when I want the same entangled state to be reproduced between Alice and Bob and Alice and Eve. And this phenomenon has very profound consequences for cryptography, and we'll see these over time. Let's just end this module by trying to understand a little bit more how we would quantify this monogamy. So there is such a thing as a measure of entanglement. In fact, there's many measures of entanglement, and we'll see some of them later in the course. You already saw one measure of entanglement, which was the Schmidt rank. This is a number that you can associate to any pure bipartite state, such that if the number is 1, the state is product. If the number is strictly larger than 1, the state is entangled, and vice versa, it's an equivalence. Now, if we consider mixed states instead of pure states, the Schmidt rank is not really something that's well defined anymore, and we need to resort to more complicated entanglement measures, and I'm not going to go into these for this module. But here are two properties that we want of an entanglement measure. The first one is that it should vanish on separable states. So if Rho AB is a mixture of product states, sum over I of Pi, Rho AI tensored Rho Bi, then the entanglement measure should evaluate to 0. That's the first required property. The second required property is that this should be a measure of entanglement. And entanglement is a truly quantum phenomenon. So it should be the case that if I have two parties, A and B, that share a density matrix, Rho AB, and if these two parties are to operate on their states using classical means only and local operations, meaning that Alice performs any kind of unitary or measurement on her system, Bob also performs any kind of unitary evolution or measurement, and even if they exchange classical information, then the state that they obtain after all these operations, call it Rho tilde AB, it should be the case that the entanglement between A and B in the state Rho tilde is no larger than the entanglement between A and B in the state Rho. So this is called monotonicity of the measure of entanglement, and it's a property that we want to hold because if it's really quantifying a certain amount of entanglement and we're only performing classical operations on the state, even involving classical communication, then these operations should not increase the amount of entanglement. So this class of operations, they're local operations and classical communication, they're called LOCC. LOCC stands for local operations and classical communication. So that's what we require of an entanglement measure. That's the really two basic properties. Now there's more properties that we might require, and one of these properties that is harder to satisfy is that the entanglement measure is what we call monogamous, meaning that it satisfies an inequality which represents the monogamy of entanglement, lets us quantify it. And this inequality would look like this. It would say that for any tripartite state Rho ABC, it should be the case that if we measure the entanglement between A and B, and we add this up with the entanglement between A and C, then this should be no more than the entanglement between A and BC jointly on the state Rho. So that's the fundamental monogamy inequality, and it's not true in any entanglement measure, but there are some entanglement measures for which this inequality is true. You'll see some in the homework, in the problem sets. Just to explain why this inequality really expresses monogamy, what it says is that if there's a certain amount of entanglement between A and BC, then this total amount of entanglement that's coming out of system A has to be split between B and C. There can be some amount that goes to B and some amount that goes to C, but these amounts are in a certain way mutually exclusive because their sum needs to add up to the total entanglement between A and BC.